Hi, welcome to day 20 of the Common Lisp series, and this is the final part on Grep. So today we'll be looking at performance optimization, actually more on profiling and tracing towards performance optimizations. So like I showed in the previous video, I did try doing some optimizations and that didn't really work. That backfired because I did write a lot of code, but that didn't really give me any improvements. So how do you approach this, right? So how do you normally do performance tuning? And there is this nice page on the cookbook which talks about a few different techniques. Now we have done a little bit before. We have looked at time before. I have used time, for instance, and this page also talks about using disassemble to look at the assembly code. We have done this also in previous videos, and also you have multiple declarations and declaims that you can use for optimizing speed and safety. Again, we have done this before. So today I'm not going to go through this. Instead, we will talk about profiling and tracing. Now, just before we start, let's just do one thing. If you see here, so far we have been building our package and running it basically from the command line. This is our repo. But if you wanted to load and run it directly from the REPL, so this is what you do. So basically, in this file, the ASD file, if you do Control C, Control L from Emacs, that would be like loading the file. And when you do that, open this, we'll see this is the Lisp. It's in Lisp mode. Those ASD file, it's in Lisp mode, and you can see Lisp load file, right? So that's what we have done. Now, if I go back to the REPL, what this means is I can actually do this QL quick load grep. So what we're doing here is we are basically first defining the system. So we've loaded this, so we define the system grep, and then we are quick loading that grep to the REPL. And once we do it, the packages, that is CL grep, will come in, which means now we can do CL grep and autocomplete. So if I do this, so the only functions that are listed here are main and grep function, because this is what we have exposed. These are the only symbols that we have exposed. And the point of this grep function is exactly to basically run the same thing just via the REPL. So if you see, I had run this earlier, so you can run this, and this is the same output that you get on the REPL on the terminal from the program, from the binary in the REPL, right? So I mean, you see here that the output, you have the ANSI escape code mangled. It's not printing correctly. I know there's something you can do to clean up this display in Emacs, but I'm not going to worry about that. So just to quickly show off the time function, though we have done this before. So now, because this CL grep function is just just a expression you're in Lisp, so you can do this and you will get the output of time the classical way, right? And you see this, it shows you the core usage and number of bytes cons and so on. So one thing to note here is it took a lot of time here. The same query is much faster on the terminal. That's because the output time is slower because it's outputting into this buffer in Emacs, and that's why you see that it's much slower. So the reason I'm calling this out is we can go to the next stage and do profiling, the tools here, SB profile and SBS prof. But if you do that from the REPL, you're going to have the same problem, and the time and the numbers you're going to see here are not going to be real, right? I mean, as in, they're not going to be what you get from the terminal. So given this problem, what I'm going to do is, so what I've done here is, if you go back into my repo, you will see that I have a few scripts here which I've set up just to do the profiling and basically run my program. Now I could have, like we saw in the video on logging, I could have made that into a compile time flag, but I just want to do a different thing here just to show off how this can be done. So there are three variants and we're going to look at all three. So let's start with basically like this page says. So there is the simplest one, which is SB profile, which is a classic per function deterministic profiler, right? So this means every single function is going to be instrumented and you're going to get the time taken for each function. So how are we doing that? So this is the script here. So what you see here is basically, I mean, this is just taking the arguments from the user, but the thing to focus on is we are loading the ASD file and we're doing this quick load grep. This is exactly what we just did in the REPL. And then finally, we're going to eval this string. And I've just put this together as a program because it's easier to manage. Now this is not the best way to do things because I can't indent stuff. It's like a string inside a string and all. But because this is a small enough code, I can do this, right? And we're going to use the SB profile package and the profile function. So this is what is basically mentioned here. But also we can open the documentation. So like the word SB shows here, this is actually specific to SBCL. It's not generic to all Common Lisp implementation, but that's fine. So the first one we're going to do is SB profile. Like we see here, there's profile, unprofile, report, reset. So these are your like API, very simple. And if you see here, it's exactly what I'm doing. I have a prog in here. The first thing I'm doing is profile, and I'm giving a string which is CL grep, and that's basically, as the documentation here says, if you can see, if you give a symbol name here, that's a function that it is going to actually profile. Instead, if you give a string, that is going to be all functions based on symbols, all symbols in that named package. So this, I'm just saying profile this entire package. And so basically then I can also set some flags if you want, because please note, when we do this, we can't run our command line flags. We can't use our command line flags, right? So in this case, I wanted to see the effect of, using the memory mode. So I can like convert this back to disk if you want the default behavior. And then we actually do our grep function. This is what we just saw, which ran from the REPL. And then I then report the results, and then I stop the profile and quit. Now, when I ran this, I did notice that this order is important, that, if I did an unprofile and then report, it didn't actually work. So that's something to call out. Now, if I run this, so basically this is the with profile.sh script. So I can run it like this. I'm doing the same query. And so you see this output at the very end. That's what we were interested in. So the thing before is the results from the actual grep functionality. And then after that, you have this profile output. So this is what is of interest here. And you see here, it's a very straightforward output like mechanism. You see the number of calls and each function and the total time taken by that function. So here it's kind of obvious, most of the time is going in grep file disk. I mean, that we understand that, right? Because the rest of it is more setup. This is the actual work. But interestingly, there are like 2239 calls, which means there are actually that many files that are being grepped, and so on and so forth, right? So you see information here, time per call. So I mean, here, like you can see, right, the 113 milliseconds is all spent here on one call, whereas here it's actually 365 milliseconds, but that's like distributed over 239 calls. So your individual call is like less than 1 millisecond duration, and there is total time and there's total information, and this also giving a report of like other functions in our library that were never triggered during this profile. And that kind of makes sense because I'm doing disk mode here, all the functions related to the memory mode, etc., are not even being called, right? So this gives you a total like idea. But do note, because this is a costly profile, so it takes it's going to instrument every function. So it's like there is an extra overhead, and there is a report here of how much it thinks is the overhead. Now it may or may not be important in your case, but something to note. And also one interesting thing you notice here is like this is the like finest granularity we have, right? You see the result of grep file disk, but nothing below that, right? And when we go to our code, we do know that our grep file, if you go to my grep file disk function, so there is things which are happening inside. We're doing many things here, right? But those functions are not reported because we only like asked to profile the we only asked to profile the symbols in CL grep package. So all those functions which are like from other packages and from other libraries, they're not even going to show up here. Now, of course, you can go back and you can add that manually, but like you can see it's a lot of work, right? So that's the like pros and cons of the deterministic profiler. So one easy way to go around this is to go to the other one, the sprof profiler. So if I go back to the SBCL page, it's the module just below that. It's the statistical profile. So the idea is that instead of deterministically looking at every single function, this one kind of does sampling. So it's just going to like take samples every now and then it's going to like note what is going on. So this way, it's actually going to like profile functions, all functions, anything that runs, right? So it will profile everything in the normal package or whatever runs, right? So that's great. It's much easier, but of course it's not going to be 100% deterministic. So This SB prof, the S prof is also talked about here on this page, but let's quickly run it. So you see that the code looks actually like very similar. The structure, we start a program and then we basically start profiling with this package. We run our actual code and then we stop profiling and then we report, right? Like I mentioned earlier, the other profile, the report didn't work. But here you have to actually stop profiling first and then you need to do the report. So that's the order difference. And then if you see the code, it's the same structure. We are like basically loading our system and then like then running requiring this package in this case and then like doing the actual profile. Now I can run that. So that's like just the other script, which means enter this, and you see the output here towards the end after the grep. So basically there's a bunch of output here. Now I don't fully understand this. There's a lot of information. I am not fully clear about what all of these details are, but you see that all the functions, like including the ones in the libraries, have been captured. So that's good. And there is information here about time and percentage. So the count, the number of calls, the percentage, and so on. And there is also this, this summary at the very top, which is talking about the number of samples. So like I mentioned, it's taken 12 samples when it was running our particular program. So in this case, look, it says 10 milliseconds. So basically the program itself ran for 120 milliseconds and it has taken a sample every 10 milliseconds, and that's why we have 12 samples, and it's just going to, like, for each of those 12 samples it's going to report like what did it see, and its picture of the world is based on those 12 samples. So it may or may not be like 100% accurate. So it's all a question of how many samples you take and how regular your program is. But towards the end of this report, you see the full report with each of the functions and the cumulative percentage and the count and similar thing as before. So I mean, I believe, I don't fully understand this, but I believe that this is a very standard format with other profiling tools. So usually self percentage talks about the time spent in that particular function, while cumulative percentage is like the time spent in that function and the functions that this function calls, right? So the total thing. And you see there is like more than 100% because you have multiple threads here and so on. But all of our like functions and library calls and foreign functions and all of it is captured. So this is like a lot more exhaustive look at profile. Okay, so we have seen the profiler tools. Now let's also look at the tracer, right? So they have two options listed here. So one is CL flame graph, other is tracer. So I played around with both and I got tracer working. So I'm going to go with that one. So the page for tracer is here. Now flame graphs are like really useful ways to understand your code and your structure. So it's a very nice thing to have. So unfortunately, this one is not on the quick Lisp distribution. So instead, you can just add it manually to your quick Lisp folder by just git cloning. So what I've done here is, if you see the quick Lisp local projects folder, I have simply done a git clone of this tracer repo, and then it's easy enough to install it basically. And now using it is like we saw with the other things. There is a setup here where we are, you see the documentation here. So I've done the exact same thing. I have basically done with tracing and I'm running my function, and then we're saving a report as a trace.json. And before that, I am doing some setup where I am asking it to store some extra information, just some configuration to make the tracer bit better. And the structure is as before. We quick load our grep package. We also then quick load the tracer package, right? And so once we are done with this, we have the tracer. So the way to run it is like before, something like this. So I'm not going to run it because I already done it. And once you have it running, you will now have a trace.json file. And now the trace.json file is something that you have to, as reported here, open with Chromium's tracing viewer. Now I have a separate video about using this Chrome tracing functionality with PyTorch. So do check that out if that, because the way you work with these traces is exactly the same irrespective of your actual application. So I'll just leave a link here or otherwise you can check it out on my channel. Now, so it's all about just opening the file. Basically, open Chrome and go to this URL, and then you can load the file, the trace file. And once you do that, you will get an output that looks like this. And let me just briefly talk about what we're seeing here. We have our default 4 process task threads. So that's what you're seeing here. And we have our result printer thread, which is what is used to print. And then we have our actual main thread, which is where the main functionality of the grep function and the grep launcher and everything happens. So these are all the functions that we have. So basically it's very easy to correlate. And if you zoom in and see this, so basically we have these other threads, the process task threads starting up, but then we actually do our file system walking here. So you see that this is where we actually queue a file. So if you click here, it's actually giving me information because I've configured it, the arguments, right? So it's telling me that this is the file that's actually being queued. And so you can see that there are other files here. So this is very useful to see the exact function and what's happening. And you can see here that once you start queuing, the other process task threads will start actually processing. So probably this one is the very first one, right? So this is the one that is running this index.page. So this one, the one that this entry went into the queue first, and then this got picked up, as you can see, from the queue first by this fourth process, right? And then you can see that these are all doing their thing, they're all working, and you can see the time just by the width of this portion. You can see the time it takes. You can see the scale up here too, and you can see how long it has taken to run some of these functions. So as expected, see, you can see some of these widths are like larger than others, and that's because the file sizes are probably different, right? So this file was probably smaller than this file, so you can see clear patterns here. And then you can use this to like kind of get an idea of what's going on. So if I like zoom out all the way, you see my total runtime is from like 0 to 20 milliseconds. So this is 40. So this is like 30 is around here. So this is like some 35 plus 37, that kind of thing. So this is the total runtime of this entire thing. So maybe if I click this grep function, maybe I will get to see the wall time here. So this is 35 milliseconds that I was talking about. And so this is the whole duration. And I was trying to do this, and I was looking at traces. I was comparing my disk version with my memory version, trying to see where there was a bottleneck and where I should actually do something to improve this runtime down from this 35 milliseconds, right? And interestingly, what I observed from this by playing around and looking through this trace file, there is this like huge gap. So you see that all of these blue boxes are individual grep files. See, some of them are like quite short, quite small, but then there is this like huge one here right in the middle. And I mean, if I click this, I might like get the idea that maybe it's because there's something wrong with this file, or like this file is very big, that's why it took so long. But then you see there's a clear pattern here that's going on here. Like it's this long duration is true on all the processes, right? And you see that it's like near identical size at the same time. And most like surprising, even the file system walker, right? The file system walker, which just looks at reads files and directories, whose like individual functions are quite short, you see that there is this huge gap between this function and then this function. So it's like the file system walker was not doing anything. And why is that? So this pattern actually makes it very clear, the fact that all our threads are not working when they're supposed to work. And that's like, also if you see here, it's like a significant chunk of time. So this is I mean, if I can click this one, maybe I get this idea that it's 11 milliseconds, and you can see that it's like around 1/4 of this total thing. And so then it turns out that this is the actual garbage collection time. Again, I have not 100% confirmed this, but I can take an educated guess based on what I'm seeing here, that this is the garbage collector which is coming in and stopping the world to do its work, and that's taking like 1/4 of a total runtime. Now that's not great. I did try playing around with the GC settings, and there's a bunch of flags and bunch of things you can do there, but I couldn't really reduce this time below this default. So I won't worry about this for the moment. So for the moment, I take it that I can't really do anything about this. It's not true. We will get back to this later. So what I'll do is I will leave grep here, though I started this exercise in an attempt to see if I could optimize things further, but we have already like done 6 videos on grep, and we have had a good run with this. So also, quite concerningly, our grep doesn't really do actual regex. That's not great. So what I recommend is I will come back to grep in a later series of videos, later, not now, and we will do this process again based on all the learnings we have had here. We will probably do a real grep with actual regex, and there we will try to use these traces to improve our performance even further. So that's it for the series on grep, and in the next videos we will go in a different direction. Let's see what we do. As before, the code, all of the code for grep is there in my website in this URL, and you can also link to this from the 100 Days of CL homepage. See you. Bye.